Good afternoon, everyone. I welcome you all to today's tutorial on the course Introductory Organic Chemistry 1 conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputri from ISER Pune. I'm your PMRF teaching assistant for the course, Deepika. I'm doing my PhD in chemistry at IIT Bombay, and now we are going to discuss a few questions for today's tutorial, which is week 6 tutorial of the course. In last week's tutorial, we had discussed a few interesting examples on reactivity of alkenes. So today also we are going to discuss a few conceptual questions on the reactivity of alkynes, some of which will be related to the questions of last week's tutorial as well. Okay, so let us move forward. First question is a theoretical question. Why are terminal alkynes more acidic than other hydrocarbons? So in earlier video sessions, we had discussed acidity, basicity, how the orbitals which are possessing the extra pair of electrons or the acidic proton can affect the acidity or basicity of the hydrocarbons. Okay, so when it comes to terminal alkynes, you can visualize it as C triple bond CH. Okay, the triple bond is present on the terminal position. So what happens when a base extracts the acidic proton from the terminal alkyne? You get C triple bond C and a negative charge at the terminal carbon. So you can visualize that the negative charge which is being formed due to extraction of the acidic proton is present in a sp hybrid orbital. Okay, c triple bond c is being formed by sp hybridization. So in the sp hybrid orbital, now whatever bond was present between carbon and hydrogen, the acidic hydrogen, that bond has been broken now, and the extra lone pair of electron will be present now in the sp hybrid orbital left. So we know that in an sp hybrid orbital we have 50% of s character and 50% of p character. So the greater percent is s character of the orbital, the lower will be the energy of the orbital. Hence, the stability of the species being formed will be more. So the driving force will be higher to generate the stable species, isn't it? So you can answer the question as the carbanion being formed possesses the negative charge on an sp hybrid orbital, which has more percent of s character, and hence leading to the higher acidity of the terminal alkyne ch bonds. So that was a theoretical question, the first question of today's tutorial. Let us move to the next question we have. Provide the structure of the major organic product or products in the reaction below. You are given butane here. This is terminal alkyne, and you have been asked to treat it with sodamide in presence of this alkyl bromide. Okay, it is benzyl bromide, and you have been asked to treat butane with sodamide followed by the treatment with benzyl bromide. So what will happen? You have to go step by step. Sodamide is a basic reagent. So what will it do? It is a strong base because in solution it forms sodium ion and amide ions. So charged species was a very strong base which we have already discussed in our session. So this will extract the most acidic proton first, which will be the most acidic proton in all these three types of protons. Of course, the terminal alkyne one. So it will, in the first step, the base will extract the proton, forming a carbon ion here. Negative charge will be oriented on this carbon, and then this negative charge will undergo a SN2 mechanism, because look at this reagent provided here, benzyl bromide PHCH2Br. What will happen? This bromine is present in a primary carbon center. Okay, so we know that primary carbon centers readily undergo SN2 substitution reaction. So in this reaction, the carbon ion generated in the first step will act as the nucleophile, and it will attack on this carbon center, the primary carbon center, and then the bromide will leave. Like, it will follow a SN2 mechanism. Like this, you can see. Like I said, the first step is acid base reaction. The base will abstract the proton and forming a carbon ion. Sodium will be the conjugate, sodium will be the counter cation, okay, of this carbon ion. And then upon addition of benzyl bromide, the carbon ion will attack on the primary carbon center, knocking out the bromide ion. And hence you get this internal alkyne as the product. I hope this was clear. Okay, so next question we have is, which of the species below is less basic than acetylide? You are given five options and you have to choose what will be the answer, that between among these three reagents provided, which one is less basic than acetylide? So for acetylide, you have to know the structure first. It is carbon carbon triple bond. Like you have to acetylide forms when you extract a proton from the terminal carbon from ethine. Okay, you take ethine, then extract one proton. You have CH triple bond C and minus charge on the carbon, which is present on sp hybrid orbital. So you have to react it with acidic substances, right? So now you have to compare the basicity of the species acetylide with these three. You know that more the S character, more the acidity, which leads to less the basicity, right? So for acetylide, since the negative charge is present in sp orbital, so since the negative charge in acetylide is present in sp hybrid orbital, it will be more acidic, hence leading to very low basicity, isn't it? And when you compare the basicity of acetylide to these three species, you will see that negative charge in A and C are present in sp3 hybridized orbital. Okay, the negative charge is present in sp3 hybrid orbital, which is less s character, leading to more amount of basicity. So answer will not be A and C for this question. Okay, answer will be either B, D, E. So we will exclude A and C. I hope you understood. So after excluding A and C, we are left with B. Let us now check whether
Hello,
STD.
ma'am. Hello, ma'am.
Yes, yes,
Ma'am, is the class is running?
yes, yes.
But I'm not getting your class, ma'am.
Is it visible now? The screen is visible. Hello, hello.
Yes, ma'am.
Okay, is the screen visible?
No, ma'am. You are presenting your screen. It is like black.
Okay. Now is it visible?
Yes, ma'am.
The slides are visible.
Yes, ma'am.
Okay, okay. Thank you so much.
Ma'am, no one is there. I am only.
Yeah, actually, the time was shifted, so no one was here actually. So I had to record it for YouTube also, right? So that's why I was conducting the class. Okay, I
Okay,
had
ma'am.
started from 3, so you can continue with the next questions, or maybe you can catch up in the YouTube channel also. Whatever three
Okay, ma'am.
3 4
Ma'am,
questions yes.
uh, what is your YouTube channel, ma'am? I don't know.
Okay, you can get the YouTube channel links in the public sheet also. And
Okay, ma'am.
the YouTube channel you will get will be tutorials by Deepika. Okay,
Okay, ma'am.
all the recordings of the previous classes are also there, you can go through those. And for today's class also you can follow the recording.
Thank you, ma'am.
Tutorials by Deepika. Maybe the screen is still shared, right?
Yes, ma'am.
Okay, so this is the YouTube channel.
Oh,
You can get all the
oh,
recordings on this channel. Okay,
thank you, ma'am.
for today's lecture as
I'm
well. Yes.
okay, ma'am. I'm working in college, ma'am. So,
Okay, right now.
yes, ma'am.
Okay, no
I'm
issue.
having class now.
Yeah, yeah, no issue. You can
Okay.
continue with the live session also, or you can go through the video recording also. Because today's recording
Sorry for
also,
the interruption, ma'am.
no, it's
And
okay.
thanks for the information.
It's okay. For today's recording also, you can go through this video YouTube channel which I showed just now. This one.
Thanks, ma'am.
Okay, no issue.
Thank you, ma'am.
Okay, no problem. Okay, so we will continue with the questions. We were in this question currently, and this acid for acetylate, we were comparing the basicity, and we saw since the negative charge is oriented on sp3 hybridized carbon for A and B, so these will be more basic. Okay, and when it comes to B, you will see that negative charge is oriented on the oxygen here. Okay, which is highly electronegative as compared to carbon. So the oxygen will not feasibly give up its extra electron pair to react with acid. So now we know that this methoxide anion is less basic than acetylate. Okay, what is basicity? The ability of giving up giving up electrons. Okay, or the ability of giving up hydroxides or react with protons. So methoxide will not readily give up its electrons. Hence, you will know that this methoxide anion generating reagent will be less basic than acetylene. So the answer for this question will be B. Okay. Then let us move to the next question, which is a theoretical question. Describe a chemical test for distinguishing terminal alkynes from internal ones. To distinguish terminal alkynes from internal ones, you can add a solution of copper, cuprous, or silver, and when you add a solution, you will see that terminal alkynes form insoluble metal acetylates and precipitate. The acidic proton is readily extracted from terminal alkynes, and you get metal acetylates which precipitate in the solution. Next, we are moving. 2-methyl hex 3-wine can be prepared by the reaction of an alkynide with an alkyl halide. Does the better synthesis involve alkynide attack on bromoethane or on 2-bromopropane? Okay, explain with reasoning. You are synthesizing 2-methyl hex 3-wine. And you have been given two options of synthesizing 2-methyl hex 3-wine either by attacking alkynide on bromoethane or 2-bromopropane. First of all, you have to draw the structure of 2-methyl hex 3-wine. Okay, the structure will be, I'll try to draw here. So you have to synthesize this molecule, and you are asked that you will attack alkynide on this bromoethane fragment, or you will attack alkyne on 2-bromopropane. Like you will attach the bromide on here or here. You are asked this. So, to synthesize this molecule, will you attack with alkynide on bromoethane or 2-bromopropane? So, clearly it is a substitution reaction. You have to substitute with alkynide on a bromide to give this compound. So, attack on the less sterically hindered primary bromide is more favorable when it comes to SN2 substitution reactions. So, if you attack on bromoethane with alkylide, with this alkynide, if you attack on bromoethane, you have a better SN2 substitution reaction because the bromoethane, for bromoethane, the bromide containing center will be less sterically hindered. Whereas when it comes to 2-bromopropane, like you are attaching bromide on this center and attacking with alkynide, you will have a comparatively higher sterically hindered center here. The bromide will be this time more sterically hindered. So, reaction of an alkynide with the secondary bromide will result mostly in elimination instead of substitution. Hence, if you want to synthesize this compound by substitution reaction of alkynide with bromoalkane, you have to choose bromoethane in this case. I hope this is clear. This concept will come from SN2 substitutions feasibility. Okay. Always remember primary alkyl halides will readily undergo substitution, and whereas sterically hindered haloalkanes will undergo elimination over substitution. Let us move to the next question now. Provide the structure of the major organic product in the reaction below. You are given an alkynide here where you have a negative charge on this sp orbital of this carbon atom, and sodium is the counter cation, and you are reacting it with a alkyl bromide. Okay. So, like in the previous question we discussed, you have two options. Okay. So, you have to react this alkynide, sodium alkynide, with this alkyl bromide. So, out of two possibilities, elimination and substitution, you have to choose which pathway will it undergo. First of all, you have to notice the alkyl halide present here. Is it sterically free or is it sterically hindered? Because we know that if steric, steric hindrance is not present in the alkyl halide, it will feasibly undergo SN2 substitution. But when it comes to sterically hindered bromide, the reaction undergoes an elimination pathway in presence of strong base. So here you see that this negative charge is present on sp hybrid orbital. That means this species, being a charged species, is a strong base and will definitely have a high driving force of being neutralized by reacting with this alkyl halide. But since it is a sterically hindered alkyl halide, the reaction will follow an E2 elimination pathway over SN2 substitution. Yes, of course, you will get a percentage of substitution product as well. You will get SN2 substitution product as well. But following the rule, if you have primary versus secondary alkyl halide, the secondary will readily undergo elimination pathway in presence of a strong base over substitution. So the major product form which will form in this reaction will be this cyclohexene. What will happen? This base alkynide will extract a proton from either this side or this side. Since it is a symmetrical molecule, so this or this the same only. So the one of these center will give up its proton for E2 substitution, and after extracting the proton from this position, the bond CH bond will break and arrow will be pushed to this carbon carbon bond, and this bromide will be knocked out, leading to the formation of major product, this cyclohexene. And this terminal alkyne will be the byproduct of this elimination reaction. Okay, and if you had gotten substitution reaction here, the product would have been this C center would bring up this cyclohexyl ring, and this bromide will knock out, but that will be a very minor product in this reaction. Then moving to the next question, provide the structure of the major product in the reaction below. You are given this terminal alkyne and you are reacting with it sodamide, a very strong base, and you are adding this cyclopentanone molecule to the reaction system after generating the first species formed in the first step. To that you add this cyclopentanone moiety, and then you work up the reaction with acid. Okay, acidic water, you work up the reaction. What product you will finally get? Let us look at the reaction path mechanism pathway step by step. What will happen in the first step? When you add sodamide, a strong base, to this terminal alkyne, the base will extract the most acidic proton first. If you look at the other protons present versus this terminal alkyne proton, definitely this one is the most acidic one, being present in the sp carbon center, and the CH bond is sp hybridized. So you will extract a proton from this center, leading to the formation of this alkynide. Okay, so after this acid base reaction, we are adding cyclopentanone to the system. So the alkynide, being a nucleophile, strong nucleophile, will attack on the electron deficient center of the cyclopentanone. So this carbonyl carbon, it is highly electron deficient, as we know, because the shared electron pair of this carbonyl CO bond is being pushed towards higher electronegative atom. So the alkynide will attack on the this carbon center of the carbonyl carbon, and leading to the formation of this anion. Okay, this will attack on the carbon and the electron pair will be pushed towards the oxygen, giving a negative charge to the oxygen atom. Now, in workup, the oxygen negative charge will quickly pick up a proton from the medium, leading to the formation of this tertiary alcohol. And these kind of reactions are in general used for the synthesis of tertiary alcohols. Okay, so I hope the reaction pathway is clear to you. In the first step, we saw acid base reaction, which produced alkyne conjugate base, which is commonly known as alkynide. And alkynide being a nucleophile, it will undergo nucleophilic attack on the ketone, giving alkoxide ion. And the alkoxide ion quickly picks up a proton from the system, giving us a tertiary alcohol. So let us move to the next question now. Provide the structure of the major organic product of the reaction below. In last week's tutorial also we saw how hydrogenation of alkenes are carried out in presence of metal catalysts or Lindlar's catalysts. So for alkynes also the reactions follow the same pathway. Okay, the alkyne and hydrogen molecules will be first adsorbed on the catalyst surface, and then hydrogenation of the alkenes took place in last week's tutorial by breaking the physical interaction which form by due to adsorption of hydrogen on the metal surface. Okay, this after breaking the interaction of hydrogen and metal surface, hydrogen atoms are transferred to the starting materials, giving you cis addition of hydrogen atoms across the carbon carbon double bond. So similarly in alkynes as well, the hydrogen atoms will first be adsorbed on the metal surface, then the physical interaction present between hydrogen molecules and metal surface will be broken down, and hydrogen atoms will be transferred one by one across this carbon carbon triple bond. And for alkynes also the addition will take place in a cis fashion, because see, suppose the catalyst surface is present here, so hydrogen atoms will be transferred from the same side only, right? So when we transfer hydrogen atom to these two centers from the same side, this cyclohexyl moiety will be pushed upwards, leading to the formation of this alkene. Okay, this terminal alkene will be formed from the alkyne. And in this reaction, if you use excess of hydrogen and Lindlar's catalyst and keep it for a longer period of time, you will end up getting overhydrogenation, leading to the formation of alkane. So for that purpose, chemists use substances which prevent such over reduction. Okay, so for this reaction, after getting cis addition of hydrogen, you get this terminal alkene as the product. Now let us move to the next question. Provide the structure of major organic product or products in the reaction below. We are now reacting this internal alkyne with sodium metal in ammonia. You are given pentyne and asked to react with sodium and ammonia, what will happen? Let us approach this question step by step. Sodium metal in amide will form first sodamide, which is a very strong base, and then sodamide will extract a proton from the most acidic center. Okay, pardon. Since this is a internal alkyne, like we saw in the other cases, we will not get a sp hybrid orbital carbanion in case of internal alkynes. So how this reaction mechanism will follow? The sodium metal will first transfer one of its electron to one carbon here, okay, leading to the formation of one carbon ion. So it has two possibilities. The sodium metal will donate its electron to either this carbon or this carbon, okay, and you end up getting two types of carbon ions, either on this position or on this position. You can first approach donating the electron one electron to this carbon atom, and the arrow will be pushed towards this side, giving a negative charge to this carbon atom, and you get a carbon ion here. Then this carbon ion will now be accompanied by another negative charge on this carbon atom as well. So the carbon ions will end up taking up protons from the system, but since you get two negative charge on two carbon atoms, which will be a highly unstable system, the will be pushed alkyl change will be pushed to different to opposite directions, so that the negative charges formed will be on opposite directions on these two carbon atoms. Hence, after taking up protons from the system, you get the alkene as the product, but the alkyl change will be pushed to opposite directions. I hope why we got the trans isomer, the reason is clear. You get two negative charges on this carbon atoms, which will lead to a very unstable system. So the negative charges will prefer to stay in opposite directions, leading to pushing the alkyl change on the opposite directions. Hence, you end up getting this trans product as the major product for the reaction. So, then let us move to the next question. Provide the structure of the major organic product in the reaction below. You have been given this terminal alkyne. On one side, you have this cyclopentyl moiety attached, and you have to react it with hydrobromic acid. So, this type of reaction we discussed in last week's session as well. So, we will approach the question in a step by step manner. You have this terminal alkyne and HBr in the system. So, this alkyne, this carbon carbon triple bond carrying two pi bonds is electron rich, so it will attack on a proton from the acidic medium, leading to the formation of a carbocation. So you have two possibilities. You will get the carbocation on either this side or this side. Okay, you will either get the carbocation system on the terminal carbon, or either on the terminal carbon or the internal carbon. So when the alkyne will take up a proton from the system, the proton will go to the terminal carbon, leading to the generation of carbocation on this center. Why? Because this is a more stable carbocation. Okay, we discussed the stability of carbocations in last week's session. This carbon center, being a tertiary one, will be a more stable carbocation in comparison to the carbocation that will be formed here, which will be secondary one. Okay, so first the proton will go here and you will get the positive charge on this internal carbon atom. Then after generating carbocation on this carbon atom, now we will attack on it by bromide anions present in the system. Okay, so bromide anion will attack on the carbocation formed on this center, giving you the Markovnikov's product as the final product. So this alkene, this bromoalkene, you will get as the major product for this reaction. And equivalent of HBr also matters for such reactions, because if you add excess of hydrobromic acid for these reactions, the product will not stay in this alkene stage. Okay, it will further react with proton, forming a carbocation on the more stable carbocation center, and then one more bromide ion can neutralize the carbocation. So equivalent provided in the question is also an important factor. I hope the reaction mechanism was clear to you. Hence, we are moving to the next question. Provide the structure of the major organic products in the reaction below. You are again given a terminal alkyne this time, and you have to react with HgSO4 and in presence of sulfuric acid. So what happens in presence of mercuric sulfate? Like we discussed for reactivity of alkenes towards such reactions of mercury, we got mercuranium mercuranium cation in the mechanism of this reaction. So let us see what happens in the reaction. First, this terminal alkyne will react with this mercuric sulfate, and you get mercuranium cation first, which will be coordinated to both the carbon atoms first. Then the water molecule will attack from the less sterically hindered side of the alkyne. After getting the mercuranium cation as the three-membered ring structure here, the water molecule will attack. Okay, so in the second step, the water molecule will attack, but first you have to form the stable carbocation. Okay, first you get the three membered coordinating reactive intermediate, then the three membered ring will open up, giving you the more stable carbocation. So you end up getting a carbocation center here, just like the previous question. You get the more stable carbocation formed on this center, and water molecule attacks in the next step, neutralizing the carbocation, leading to the formation of this enol. But this enol will not be a stable form of this compound, because this oxygen atom lone pair is continuously in conjugation with this carbon carbon double bond. So it quickly rearranges to its keto form. Okay, by ketoenol tautomerism, the product obtained in this reaction will be converted to ketone quickly. So the major product formed in this reaction is this ketone. Okay, so in the next question we will see ozonolysis of alkynes. In last tutorial we saw that how ozonolysis of alkenes went ahead, and in that case we first observed molozonide, which rearranged to a more stable ozonide, because due to presence of three oxygen atoms simultaneously, the molozonide species formed in case of alkenes was highly unstable, so it rearranged to form a more stable ozonide, and then we reacted with dimethyl sulfide in last week's example, and then we opened up the ozonide by oxidative cleavage, leading to the formation of two carbonyl compounds. So let us see how alkynes react with ozone. Okay, so first the carbon carbon triple bond will undergo a 3 plus 2 cycloaddition kind of reaction, or you can say or you can say this oxide will attack on this carbon atom of alkyne, then this carbon carbon triple bond will now attack on this oxygen atom of ozone, and the arrow will be pushed to the middle oxygen, neutralizing it. Okay, so this 3 plus 2 cycloaddition reaction will happen in the first step, leading to the formation of this molozonide, which contains three oxygen atoms simultaneously, two of which are directly linked to the carbon atoms of the alkyne. Now, this molozonide, being a very highly unstable species, will undergo breakage. The ring will be opened, and it will now rearrange to a more stable ozonide. Okay, this ozonide is, when compared to the first molozonide formed, will be more stable, and in the subsequent step you will open up this ozonide formed with water molecule, Okay, the water molecule will first open up the ozonide by attacking on oxygen atom, and this four membered ring will first open. Subsequently, this carbon oxygen bond also breaks, leading to a negative charge on this oxide, and you end up getting this dicarbonyl species. So, in the later stage of ozonolysis of alkynes, we treat this dicarbonyl compound with hydrogen peroxide, which will lead to the cleavage of this carbon carbon bond. Okay, this carbon carbon bond is already very weak because both these carbon centers are highly electron deficient, because the oxygen atoms present here are pushing the shared electron pairs towards each of themselves. Okay, so this carbon carbon bond will be cleaved using hydrogen peroxide, leading to the formation of two molecules of carboxylic acids. So thus, when it comes to alkyne, when you treat alkyne with ozone, unlike in case of alkenes where we got two molecules of carbonyl compounds, here we get two pairs of carboxylic acids. And the last step in which the dicarbonyl compound is oxidatively cleaved plays a important role in this mechanism. Okay, so let us move to the next question with this. Propose a plausible arrow pushing mechanism for the following reaction. You are treating this terminal alkyne with bromine water. First, you have to know what will be the product and how will it form. What kind of mechanistic pathway will the reaction follow? The product here is already given to you, that when you treat this terminal alkyne with bromine water, you will get this alpha bromo ketone. Okay, so how is this ketone formed? Let us see. The carbon carbon triple bond, being electron rich, will first attack on one bromine atom of one bromine atom, leading to the formation of this bromonium ion. The reaction is similar to the same as how alkene and bromine react. In that case as well, we got such kind of bromonium ion. Just the difference is this time you have this carbon carbon triple bond as a member of this three membered reactive intermediate formed. Now what happens? You have this bromonium, water molecule will attack on the system to open this three membered cyclic intermediate. Now you end up getting this oxonium ion in the next step. And after removing a proton, you get an enol as the product here, till here. Okay, this enol first forms. After the formation of enol, Since it is not the most stable form of this compound, it will quickly undergo ketoenol tautomerism to give you the keto form of this compound. So, hence, you get this product as the major product. Here in this step, you have two possibilities. Okay, the water molecule can attack on the bromonium by either this side or this side, but you can visualize it by the formation of the more stable carbocation which is being formed here. So what will happen before the water molecule attacks? You get a carbocation either here or here. Okay, so the carbocation generated on this side will be more stable. Hence, the water molecule will preferably attack on this carbon center. Also, you can also rationalize it by the presence of phenyl ring here. Okay, phenyl ring being planar will not cause much steric hindrance as compared to this carbon center, but this being an electron with slightly electron withdrawing species will make this position more electrophilic. Okay, hence water will preferably attack on this more electrophilic center, leading to the formation of this oxonium species. Okay, so you end up getting this enol and this ketoenol as the major product on the for the reaction. So with this, we have discussed today's questions on the topic reactivity of alkynes. Let us quickly go through the questions which were discussed today. We started with the first theoretical questions: why are terminal alkynes more acidic than other hydrocarbons? We approached the questions by the fact that the carbon ion which is generated upon deprotonation of terminal alkyne contains the extra electron pair generated in an sp hybrid orbital, and if the extra electron pair is being contained in an sp hybrid orbital which has 50% of s character, leads to higher acidity of the parent species. Okay, so since for terminal alkynes the newly formed extra electron pair is present in sp hybrid orbital, the terminal alkynes will be known as more acidic. Okay, more the s character of the parent species, more will be the acidity, and in turn less will be the basicity. Always remember. Then we moved to this reaction and we approached what kind of product we got and how, what kind of reaction mechanism was followed here. We saw that the strong base sodamide being a very strong base will extract the most acidic proton of this substance, leading to the formation of alkynide, and then it will undergo a SN2 substitution reaction because we have a less like sterically free alkyl bromide here. So we looked at the mechanism in this way. The second step of the reaction followed an SN2 mechanism on this primary carbon center. Then we compared the basicities of these three compounds to acetylene, and we saw that the negative charge present in the A and C species were in sp3 hybrid orbitals, whereas for acetylene it is sp hybrid, so more acidic and less basic, isn't it? So A and C were more basic than acetylene, whereas when it came to methoxide and ion, we saw that oxygen being highly electronegative, it will not give up its extra electron pair very easily. So B was the correct answer for this question. Okay, since oxygen is not wanting to give up its electron, it will be less basic. Then we also discussed this theoretical question, how you can distinguish terminal alkynes from internal alkynes, and the answer comes from the higher acidity of terminal alkynes. Okay, what happens when you treat with metal ions, you have you get metal acetylenes which precipitate in the solutions, but terminal alkynes do not contain such strong acidic proton, and hence they cannot react with metal solutions to give you metal acetylenes. Then we saw which method was better to synthesize 2-methyl hex 3 wine, whether you will attack the acid the alkynide on bromoethane, like bromide attached here, and you will attack with this carbon, or bromide will be attached here and you will attack with this carbon. And we saw that to synthesize this molecule using substitution reaction, you will need a haloalkane which has primary carbon center. Okay, because for the secondary one, you will get a steric hindrance as compared to the primary one. So we saw that attack on the less sterically hindered primary bromine, which is bromoethane for this case, is more favorable. So it was preferred to form the given molecule 2-methyl hex 3 wine by attacking alkynide on the less hindered bromoethane. In the next question, we were given this alkynide and we were asked to identify the major product if we react it with this alkyl bromide. We saw how we had two possibilities, substitution versus elimination, but since we had this sterically hindered haloalkane, we got elimination reaction in this case. Okay, we have strong base here and we have the sterically hindered haloalkane. So E2 was preferred over substitution, and this was the major product form. Then in the next question, we saw how this terminal alkyne reacted with sodamide to form an alkynide on this carbon center. Then we added cyclopentanone to the system, and this alkynide attacked on the electrophilic carbonyl carbon center, leading to the formation of this oxide anion. And this oxide anion was neutralized during workup stage. Okay, it just simply picked up a proton, giving us this tertiary alcohol. Then we discussed hydrogenation of alkyne in presence of Linder's catalyst, and we observed that this alkene was formed. Similarly, when we reacted this internal alkyne with sodium in ammonia by following a single electron transfer mechanism, we saw that dianion species was being formed and the alkyl chains were being pushed in the opposite directions to give you this trans isomer of this alkene product. Then we saw how alkynes react with AGPR, and it followed the exact same mechanism as the alkenes did. Okay, and we ended up getting this Markovnikov product. And in case of this reaction, we found that for alkynes also they follow the same mechanism like alkenes. And first we got this enol as the product after the attack of water on the mercurium ion, and then it quickly rearranged to the keto form, the more stable keto form. Then we found how alkynes undergo ozonolysis, and uh, you have to remember that for alkenes we got two molecules of carbonyl compounds, but for alkynes we get two molecules of carboxylic acids by oxidative cleavage of this dicarbonyl compound. Lastly, we tried to figure out the arrow pushing mechanism of this reaction, where we reacted this terminal alkyne with bromine water, leading to the formation of this alpha bromo ketone. So hence we have arrived at the end of this tutorial. Thank you all for joining. You will get the video recording of today's session on the YouTube channel. I'll show you this on this YouTube channel. You will get the recording of all the sessions that has been that have been taken till now on the various topics. Okay, so today's tutorial also you will get on this channel. So thank you all for joining.